Hello everyone, my name is Jiang Junwei. Today I will present my final report on fiber optic sensing. I will cover three different topics. Let's start with the first one, distributed fiber optic sensor for roller monitor. First, how does the technology work? The best principle is simple. We send light pulse into the optic fiber as the light travels some of this bonus back. This is called backscatter signal. This signal can change depending on vibration and temperature. By analyzing this change in real time, we can understand what is happening along the track. This fiber acts like a long continuous sensor. We use two main methods. First is DAS, or distributed action sensing. Is checking vibration, sound, and track movement. Second is DTS, or discharge temperature sensing. This helps us detect first risk of overhead equipment. For structural health, the fiber can monitor breach and tunnel. It can detect strands, cracking, and the concrete, and sudden temperature changes. This helps keep the infrastructure safe. Another important application is security. The system can detect if someone is in charge of the tracking of someone is trying to steal the cable. It acts like a lone security camera but using vibration. Let's look at case study regression roller monitor. Over a long period, the ground under the tracking might move. The system can detect this long-term change, such as tracking settle or deformation, before this becomes dangerous. It can also detect electrical problem. If there's a short circuit on the railroad, the temperature will rise instantly. The fiber sensor detects this real-time, allow for a quick response. So why use fiber instead of traditional sensor like a accelerometer? Accelerometer give high resolution, but they are very expensive and only cover the spots. Optical fiber sensor provide good resolution, cover a very wide area, and has a much lower cost overall. Finally, for the section, we can monitor gray hazard, for example, in area with grippers layer, cavitated or skinless, might from underground. Fiber sensing creates a 3D model of the surface every day. It can detect very small velocity change around 5%, give us an earlier warning before its gain-hole compass. Now I will move to second topic, the long track profiler, or LTP 2020, is about measuring mirror with very high precision. We already have a profiler, but there have some limitation. Let's look at a problem with the current technology. The first limitation is wobbling. As the sensor moves along the track, it's shaking slightly due to mechanical imperfection. This shaking at the false title error of our measurements. We need to fix it. The second limitation comes from the autocollimator itself. The error inside the device change depend on the distance. Standard calibration cannot fix the because the distance change constantly during a scan. To solve this problem, we introduced the LTP 2020. You can see the new ground system here. It uses a dual carriage design. This allows to run two different sensors at the same time without the interference with each other. Here is the optical layout. On the left is old vision, and the right is new LTP 2020. It looks complex, but the main goal is to accommodate the new sensor. Sensor 2 is most critical innovation. It's a customized autocollimator. While the hardware is faster, the real scatter is the software and customization. Here is the result of the customization. Usually, this device uses a built-in routine, but we accept the raw image detect data directly from the CCD camera, but apply a new correlation-based algorithm that solves the distance error problem. As you can see in the graph, the error is reduced by 5 times. The system has different operation modes. Mode 1 is simulator cross-check. Because we have two sensors of the grain trace, we can measure the scent mirror with both sensors at the same time. This confirms that our data is correct. Finally, mode, mode 2 addresses the first problem I mentioned, wobbling. By using the gradient measurement method, we can cancel out the mechanical shrinking. This gives us a wobbling-free measurement. Now let's move to the final topic. Femtosecond laser encrypts optical fiber components. I will explain the fabrication technology and the resource. We use a technical plane-by-plane inscription in create waveguide and gating inside the fiber. There are two steps. Step 1 we write cladding waveguide. Step 2 we inscribe the grating inside the core. The method is very flexible. Okay, the second one is the number sensor. Using the technique, we create a new type of blending sensor. It's used as Mazender interferometer structure. The graph graph here to show the wavelength shift. The result is amazing. It's 700 times more sensitivity than the standard Bragg gating sensor. We also apply this to temperature and humidity sensor. As shown in graph, the sensor tracks humidity very accurately. It also has a high temperature sensitivity of 800 picometers per degrees Celsius. Next, we apply this to fiber laser. Here is the experimental setup. We use a spatial components at 55 minus degrees tidal fiber breaking grating is in TFEG. This acts as an inline polarizer. It allows the laser to achieve more locking through a mechanism called nonlinear polarization protection is NPR. The performance of laser is excellent. Figure B shows the pulse width is very short, only 862 per millisecond. Figure C shows the stability. The signal-to-noise ratio is over 90 dB. This means the laser is extremely stable over a long time. To conclude the section, we achieved three major results. First, the plane-by-plane technique proved the two extremely versatility. It allows us to write both waveguide and grating into various types of fiber activity. Second, in sensing our new MZI binding sensor demonstration a sensitivity 700 times higher than standard braid gating sensor. It also performs well for temperature and humidity sensing. Okay. And third, the laser we successfully utilized a 55 degrees tidal FPG. This allows us to build a mode-lock laser and both ultra-fast and highly stable over long period. That's running into the end of my presentation. Thank you very much for your attention.